Okay, this time we're starting in Chapter 10, so it's going to be Section 10.1. And I move the screen down. So 10.1 has to do with molecular geometry and chemical bonding. We're not going to do much of 10. There will be some, but not a whole lot. So parts here. Section 10.1 is Section 10.2, definitely. But I'm going to pick out small pieces of the rest of the sections. So basically, the shapes of the molecules are decided by their electronic structures. We're going to be looking at molecular geometry, which is the shape of the molecules determined by the relative positions of the atomic nuclei. And the one that we are going to do is called the VESPR method, valence shell electron pair repulsion model. It predicts the shape of the molecules and ions by assuming that the valence shell electrons are arranged around each atom such that the electron pairs are kept as far apart away from each other as possible, therefore minimizing the electron pair repulsions, and is pronounced VESPR. So this is showing two different molecules, have boron trifluoride, and boron trifluoride does not have any lone pairs around the electron. It's one of the exceptions to having less than 8. And the other one is phosphorus trifluoride, and it does have a lone pair of electrons that are not drawn here. So the difference in the angles here, this 120 versus the 96, is because this one has an extra pair of electrons, and that has made all of the pairs come in closer together. Okay, so you can see here spatial, this is all what they call in the plane, they're all on the same level, whereas this one forms more of a pyramid-looking shape, and I have a lone pair of electrons over here. So all the atoms are pushed further in this direction to give more room to the electron pair, which is not shown there. In looking or predicting molecular geometries, there are families and then there are the shapes. Okay, you have to have at least 3 atoms in order for there to be a geometry, because anytime I have 2 atoms, it's basically just a linear shape. Okay, think about drawing 2 dots between a paper. There's always going to be a line between them. So 3 is the minimum amount I have to have in order for their 3 total atoms is the total number that I have to do a geometry. So here I have families. The families are linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. So linear, and all of these are assuming that I have an inside atom plus then something else. The book also talks about these as being bonding pair. I like to use the word outside atoms, and I'll get to that, why that is, in a few minutes. Okay, but on a linear, I have 2 outside atoms, and of course on all of these, and the inside atom, or the center atom. Okay, for trigonal planar, I have 3 outside atoms and the center atom. I also have 2 outside atoms and 1 lone pair. And I'm going to abbreviate lone pair of electrons because that was taking up too much of my slide space as being LPE. So you notice that for both of these inside this family, the total number of electron pairs around the center atom add up to be 3. Okay, so 2 and 1 is 3. I have tetrahedral. Tetrahedral has 4 outside atoms, has 3 outside atoms and 1 lone pair, 2 outside atoms and 2 lone pair. And again, this whole family adds up to have 4 electron pairs outside the central atom. Trigonal bipyramid, go up here. Trigonal bipyramid has 4 possibilities. Again, 5 outside atoms, 4 outside atoms and 1 lone pair, 3 outside atoms and 2 lone pair, and 2 outside atoms and 3 lone pair. And the case for all of these is that the outside pair, the electron pairs around the center atom add up to be 5. And on octahedral, there are only 3 members of the family. Could possibly be more, but we're only doing 3. 6 outside atoms, 5 outside atoms and 1 lone pair, or 4 outside atoms and 2 lone pair. So the ones lower than this, we're not going to worry about what they are. Okay. This is showing the families and how they look. I have linear. It's called that because they're 180 degrees apart from each other. So it's just 3 atoms in a straight line. I have a trigonal planar, so here's my inside atom with 3 outside, and they're all flat. This is all in the same plane, so this is a 2-dimensional figure right here. I have tetrahedral, which is a center atom, and then I have 4 outside atoms. Tetrahedral comes from the word 4-sided, okay? And so, again, that has 109.5. And this is a three-dimensional, so this back line back here is going into space. And this line here is coming out of the page. I have trigonal bipyramid. It's named by such that if I look here, 1, 2, 3, that forms a triangle. And then I have a pyramid sitting above it and a pyramid sitting below it. So basically it's like taking this structure and that structure and melding them into one. Or basically I rotate this by coming in and out of that A. Okay, so here's the linear and here's the trigonal planar, and I add those together. And then I have octahedral, which stands for 8-sided. It's also two pyramids stacked on each other, but the difference is that the base of the pyramid is a square. I've got 1, 2, 3, 4, and a triangle or a pyramid above and a pyramid below. All these angles are 90 degrees. Okay, these are 120, just like these are, and this is a pyramid standing above there, so that's 90. If I add the two 90s together and come all the way back, there's my 180 from the linear. This is it in a balloon model. So if I just take balloons and tie them together, here's linear, here's the trigonal planar, here's the tetrahedral. Okay, so you see that these are all sitting flat, and if you look carefully, this end of the balloon is actually a little bit higher than this end compared to this picture over here. The trigonal bipyramid, okay, the green would be represented by these two balloons. These three balloons are represented by these three balloons. So that's what I said, if you melt the two structures together. And octahedral is, here's my square, and a pyramid above, and a pyramid below. And some examples of those. Alright, so when I ask, however, I'm going to be asking for the molecular geometry. So I'm going to be asking for this list right here. I'm not going to be asking about what the family is. I'm going to be asking about what the molecular geometry is. Okay, so this uses the term bonding. I use outside atoms, and it's because a double bond and a triple bond and a single bond are all directions of the central atom, so they are treated the same. Okay, so when I have two outside atoms and 0 lone pair, I have linear, which is the smallest I have, because again, if I go back to 2, it's automatically linear. I have 3 and 0, which is trigonal planar. The one with 0 lone pairs for the molecular geometry is the same as the family name. Okay, so trigonal planar, tetrahedral, tetrahedral. Okay, then I have 2 outside atoms and 1 lone pair, and that becomes bent. Here's my lone pair of electrons. I have the tetrahedral family, has 4 and 0, so tetrahedral. A trigonal pyramid. Okay, so this is a triangle, but this green is actually sitting above the plane of those, and my lone pair. And here's my second bent. So I have 2 bents. I have a bent that's a 2 and 1, and a bent that's a 2 and 2. I highly suggest taking note cards and on one side putting down something like 3 outside atoms, 0 lone pairs is a trigonal planar. 3 outside atoms, 1 lone pair is a trigonal pyramid. And put this on one side of the note card and put this on the other side of the note card, and that way you can memorize it because it is basically memorization. Okay? To go to the 4 family, which is the trigonal bipyramid, there was 4 different possibilities. The 5 and 0, so again, that one is the same as the family name. A 4 and 1. Now, the whole idea is I want to minimize the angles between them. So if this is 120 and this is 90, if I took this one off, it would be 90 for all of them. But if by taking this one off, the triangle one, then it's 120, 120, and still 90. So this is the one that gives me the least amount there. Okay, it's called a seesaw because if you think about these 2 atoms here being the base of the seesaw, and this would be where you would sit on it, because this is basically, it appears as empty space. Okay, so you would sit here, and it would teeter-totter back and forth. Okay, T-shaped. I'm going to continue taking off of the central triangle here, so I take off 1 here and 1 there, and so this is the top of the T, and this is the leg going down to the ground. If you turn your head 90 degrees like that, you will see it. Linear. Now I take the 3rd one off here, and so I'm just left with these, and so that's linear. So I have 2 linears. One is 2 outside atoms, 0 lone pair. The other one is 2 outside atoms and 3 lone pair. The last family is octahedral. Again, 6 and 0 is octahedral, the family name. 5 and 1. Okay, all of these angles are 90 degrees, so it doesn't matter which one I choose. So either way, no matter which one of these I choose, I can turn it to be this way. Here's my square, 1, 2, 3, 4, 1, 2, 3, 4, and here's my pyramid, so it becomes square pyramid. If I take off 180 degrees from there, I get still square, 1, 2, 3, 4, but now it's all in one plane, or it's all two-dimensional, so it becomes planar. Okay, so those are the shapes. And it really is memorization. You would want to put 4 outside atoms on one side, 4 outside atoms and 2 lone pair on one side of the note card, square planar on the other side of the note card, and practice. So predicting, determine how many electron pairs are around the central atom. Double bonds and triple bonds count as one pair. That's why I tend to use the term outside atoms, not electron pairs. If I have a resonance structure, just choose one of the structures because of all the structures will have the same geometry. I skip number 2, which is choose the main group because I don't want you to name that one, and then choose the shape or the molecular geometry from the number and location of the lone pairs. So the example I have is predict the geometry of the following molecule using the VESPR model. It's arsenic trichloride. I gotta move this back up. So going through how to obtain the Lewis formula or Lewis structure, I have my skeleton structure with arsenic in the center because it's listed left. It's leftmost here, becomes center here unless I tell you otherwise. Calculate my valence electrons. So I have arsenic has 1 times 5 is equal to 5. Chlorine, I have 3 chlorine atoms and each one's 7, so that's 21. That gives me a total of 26. I put around 3, I'm going to make 3 bonds here, here, and here. And when I do that, I subtract 6, and that leaves me 20. And then I'm going to count around as I put my lone pair around the outside atoms. So 2, 4, 6, 8, 10, 12, 14, 16, 18. So I used up 18. That leaves me 2. Where did those 2 have to go? Onto the center atom, not as a bond. And so it looks like that. So that's the Lewis structure. Next part is now I want to do where my electron pairs are. Okay, so I've got 1, 2, 3 outside atoms, or 3 bonding pair. I have 1 lone pair, which is above the arsenic. And so the molecular geometry for 3 bonding pair and 1 lone pair is a trigonal pyramid. Next. All right, predict the molecular geometry of xenon tetraoxide. Doing the Lewis structure. Okay, I have xenon in the center and 4 oxygens. Xenon in the center because it's leftmost here. Doing the valence electrons, xenon has 8, so 1 times 8 is 8. Oxygen, there's 4 atoms, each one 6 electrons, so that's 24. So that leaves me 32 to start with. I put in 4 bonds, which is those 4 there, and that used up 8 electrons. That leaves me 24 electrons. Then I count my outside pairs as I go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. And I'm out of electrons, so that structure is done. Now I need to look at to do the geometry. Okay, I've got 4 outside atoms, or 4 bonding pair. And I have 0 lone pair. There's nothing on the xenon by itself. And so that is a tetrahedral. So there's really no way but to tell you to memorize this, unless you're really good. There are cases that if you can be really good with picturing them in your head, that you can do that. Okay. 36 is an ion. Okay. Predict the molecular geometry of the following ion. It's sulfite, SO3 2 minus. So my structure is sulfur in the center with 3 outside oxygens. Getting my valence electrons, sulfur, there's 1 of them, and that's 6. Oxygen is 3, times 6 is 18. But this is an ion, so I have 2 additional ones because of 2 minus there. Alright, and that gives me, again, 26 electrons. Alright, I put around my bonds. So when I draw 3 bonds, I use up 6 electrons. I was running out of room, so I had to go right. Okay, then I count in my outside atoms. 2, oops, that gives me 20, sorry. And then I count in my outside atoms, 2, 4, 6, 8, 10, 12, 14, 16, 18. So I do 18, that gives me 2 more. So it goes on the center atom to be like that. Okay. I have 3 outside atoms. Oh, oops, I'm sorry. This is an ion, so I have to put the charge there. So I put a bracket with a 2 minus. Okay. I've got 3 outside atoms, or 3 bonding pair. I've got 1 lone pair right here. And so 3 bonding pairs